Ngalakin Khadijan Nyunga Boja.
I mean, in the old days, you know, we had mid-year tests and things like that, but you always, because unless you could borrow someone else's notes, which some people had to do, you know, you would come to it because you didn't want to, you know, if you get behind, everyone knows, if you get behind in engineering, you sunk. Because you can never catch up. Yeah. And that's the danger of not at least keeping it going. I mean, you've only got a couple of hours, so the question is, with your other tests, you know, where they fit in there.
2 minutes, so I'll go first, and then
when you're ready.
When I'm
One of the questions we had, I was going to talk to a colleague that used to work with me at SECRA, who's at Murdoch University, and one of the things they said was, well, with all this stuff here, you actually get people to students that come to attend.
Yeah.
They were questioning about whether, I think there needs to be, you need to actually have a requirement, you know, there should be a requirement to actually attend at least 80% of the lectures or something like that.
Yeah. That'll force students to come to lectures.
Oh yeah, just do a sheet. Well, when I did an MBA, we had this Professor Moore from here, and he said that you guys are all pretty good. You've done, you know, you're graduates. You're all pretty good. You know, with this stuff. What about if I could give you all A's right now, and we get stuck into the order? What he said was, the problem with that is because everyone's busy. If you knew you had an A, he was trying to get people to really focus on the work and forget about the marks, but really learn. And that's the problem. So everyone's busy. So if you knew you had an A there, then you would you naturally will prioritise something else. And that's what he said. So in our lectures, we actually have to read a stack of material each week. Yeah, it was like that. So a case study in strategic management.
I'll start.
Okay,
All right, it's 3 o'clock, so I better start the lecture. And actually, no one's online connecting to Zoom. Anyway, it doesn't matter. Is it a busy week? Okay. All right. We in this chapter we are talking about load flow, right? Trying to determine voltages and currents in a complex network. And we have already talked about the Gauss-Seidel technique. And we're going to look at another approach to do the same load flow calculations, and that's the Newton-Raphson method. We're going to use the Newton-Raphson tool. It's a mathematical tool that allows us to solve nonlinear equations, and we want to use that technique to solve the nonlinear power flow equations to find the voltages and currents in a complex network. So I think I did talk about this in the last lecture, Newton-Raphson method. So you have a set of equations, fx equal to 0, right? Fx equal to 0. You have these equations, fx equal to 0. We want to solve for x. And obviously, if you're going to talk about load flows, this x would be the voltage, magnitudes, and angles at the various bus bars. That's what we're trying to determine. So if we don't know the voltage magnitude, we want to know that. If we don't know the voltage angle at that particular bus bar, we want to know. So that the x is the unknown vector will constitute those variables. So fx equal to 0 is the equation that we want to solve. It's a nonlinear equation. We're going to use the Newton-Raphson method. How are we going to do that? We initially going to assume a solution for x, which is x equal to x0. So when we substitute x equal to x0, more often than not, x0 may not be the correct answer. So fx0 is not going to equal 0 because x0 may not be the answer, right? And the objective is that initial guess x0, we want to refine it through an iterative process. And how are we going to do that? We're going to do that by considering the Taylor series expansion around x0. So what is the Taylor series expansion of f around x0? We write that down. So Taylor series expansion around x0 is going to be fx0, first derivative of f evaluated at x0 times the deviation of x from its original. So we know fx0 is not going to be, fx0 is not going to be, fx0 is not going to be the correct answer. So the correct answer that will make the function f0 is fx plus fx naught plus delta x, right? So delta x is actually the deviation from the exact solution. So we're writing the Taylor series about x0. So Taylor series around x0 is fx0 plus the first derivative of f evaluated at x0, right, times that deviation delta x. So h here is the deviation delta x from the actual solution, plus some higher order terms, right? The second derivatives, the third derivatives, and so on. We'll ignore the higher derivatives. So we basically have this equation. We have this equation 0, because this term here is 0 on the left-hand side. So we have the equation 0 equals fx0. fx0 is not 0, it's some value, epsilon. So plus the first derivative of f evaluated at x0 is the Jacobian matrix, right? J times delta x. Delta x is the deviation of x from the actual value. So that's the equation. So that's what we're going to use. So what that means is once we've made our initial guess, x0 is our initial guess, and we want to refine that. In other words, we want to know what delta x is. We can use this equation to compute delta x. So delta x would then be equal to the negative of the inverse of the Jacobian times the epsilon, right? So that x plus delta x is then a more refined solution, and then we can continue that process iteratively until we are happy that the solution we have doesn't change that much, right? That's the technique. So I said that x is the unknown, and for power flow calculations, it will be the unknown bus voltages and voltage angles. For every single bus, except the slack bus, we don't know the voltage angles, right? For all the load buses, we don't know the voltage magnitudes and angles. So those will constitute our unknown vector x. Okay? So it's important that when we do these calculations to truly understand what do we know, what do we don't know, what constitute x, and so on, which I'm explaining to you now, right? So all that is the same. So this is a simple example, because we know that Newton-Raphson method is actually a mathematical tool. It's not just there to solve load flow equations. It is there you can solve any nonlinear equation. So here we're looking at, well, how can we use the Newton-Raphson technique to solve an equation, a nonlinear equation like x squared minus 2 equal to 0. Why we choose that? Because we know the answer. Answer for f is plus or minus square root 2. We know the answer, but we can assume we don't know the answer, and we try to use the Newton-Raphson technique to solve this. So we need to know the first derivative of f. So we've written the equation in the form fx equal to 0, and fx is x squared minus 2 equal to 0. So the first derivative of the first derivative of f is 2x. We simply differentiate f with respect to x. So then we know our refined solution is the previous guess plus delta x. And how do we find delta x? Delta x is the inverse of the Jacobian times minus epsilon. In other words, f evaluated at our initial guess. So f evaluated at our initial guess is this term here, and this is the minus sign. Right? Yeah. So then we have our initial guess. Initial guess is 1. Right? We can calculate delta x based on that formula. So delta x will then turn out to be will be 0.5. So our refined solution is 1.5. X, our previous guess plus delta x. Now we can continue the process. We can then again calculate delta x using our refined solution of 1.5, right? And that new delta x will be this figure here. Then what is our refined answer? Refined answer would be 1.5 times this plus this is this value here, right? And then we continue. We continue the iterative process. We continue the iterative process because we have an expression for delta x. Delta x is the correction that we make for the answer that we currently have. Right? And if we go through the iterative process, then the answer converges to 1.414, which is square root 2. Answer converges to the correct answer, which is square root 2. Right? Okay. So, Newton-Raphson, how do we apply to solve the power flow equations? Firstly, what are the power flow equations? Well, we have n nodes, right? For each of the nodes, we can write power balance equations, right? What is the power balance equation? Because each of the nodes, you got to have this picture in your mind. You can imagine some external device connected to each of the nodes. So you have an electrical network with nodes, yeah? So it's a network. And for each of the nodes, now imagine there are devices connected to each of the nodes. What are these devices? These devices can be generators. Generator can be connected to a node. What are another device that can be connected to a node? A load. A load can be connected. So if it's a generator connected to a node, right, then we say a generator bus, we know the voltage magnitude and we know the active power injection. That's what we say. So, in the Newton-Raphson method, what we are trying to find is the voltage magnitude and phase angle for that particular node. So, if it's a generator bus, we don't need to find the voltage magnitude. So, for a generator bus, there will only be one unknown, which is the voltage angle. That's it, right? For load buses, we have two equations. We have two unknowns. What are the two unknowns? Because we don't know the voltage magnitude and voltage angle both for load buses. So for load buses, there will be two unknowns that we are trying to determine, right? So for load buses, we know how much active power and reactive power the load is drawing. Yeah. So that active power and reactive power that load is drawing has to flow through the lines that are connected to that bus, right? Yeah. So when we write the equation, power balance equation, we are telling the power, active power and the reactive power that is flowing in the lines connected to that load must equal what's being drawn by the load. That's the two power balance we are talking about. Yeah. So for the two unknowns that we are trying to determine, we can write two equations. Right? We can write the active power that is flowing in the lines must equal the active power drawn by the load. Right? So that's one equation. So we can write that in Newton-Raphson form. What is the Newton-Raphson form? Power that is flowing in the lines minus the power drawn by the load must equal 0. Because then I have Fx equal to 0. Right? Yeah? And I can say the same thing. The reactive power flowing in the lines into the node minus the reactive power drawn by the load must equal 0. Right? Those are the two equations. And for those two equations, we have two unknowns, which is the voltage magnitude and the phase angle. But for generator buses, we only have one unknown, which is the voltage angle, because voltage magnitude we know. And we don't know the reactive power injected by the source into the node. We only know the active power injected by the source into the node. So we only write one equation. We say, right, the active power injected into the node by the generator minus the active power flowing out of that node through the lines must equal 0. Again, we have Fx equal to 0. So I think it's important that you understand that. Yeah? Because if you understand that and you see the equations on a formula sheet, you know what's going on. So if I tell you here, this summation, you have Pix summation k equal 1 to n, the rest of the terms, right? What do those represent? They represent the active power that is flowing out of the nodes, right? Active power that is flowing out of the nodes from node I, right? How do I know it's node I? Because we are talking about Pi. So we're talking about node I. So when you look at this equation, you need to relate this equation to the actual network. Because if you can't relate this equation to the actual network, then you're just looking at some symbols, right? And I'm going to say this, there is an n there. So this n means there are n nodes, right? So the node I can connect to n nodes, right? So these are the powers, active powers that are flowing from node I into the other n nodes. But of course, there may not be a line connecting a node to another node. In that case, that part of the expression in the summation will disappear. It won't be there, right? Because the admittance of the line will be 0 for that. So, so that's what we have, right? Because, yeah. So the second one is Qi. Again, Qi are the active power, reactive power that is flowing in the lines. So notice this equation here. So we are saying here Pg1 minus Pd1, right? So if you are looking at node 1, we Pg1 minus Pd1. So Pg1 will be what a generator is connected to node 1 and that is injecting some power, Pg1, some constant, right? Pg1 will be a constant. Minus Pd1. What is Pd1? So that particular node, we are telling there is a load connected to that node as well. I mean, if there is no load connected to that node, well, Pd1 will be 0, right? So Pg1 minus Pd1. So Pg1 is the active power you are injecting into the node. Minus Pd1 is a active power you draw out of that node. Must equal, right, Pix. What is Pix? P1x. What is P1x? Well, P1x is all the active power that is flowing out of, node 1 into the various other nodes through the lines that are connecting node 1 to the other nodes, right? So Pix represents the power flow inside the network, right? That's important to understand. And same with Qix, right? So Pgi minus Pdi or Pg1 minus Pd1, in general Pgi minus Pdi is a constant, right? It's what a generator or a load will consume, right? What a generator will inject into a bus and what a load will consume. Okay? So I think if you know that, then I think it's easy, right? So here it is. P1x, if I can ask you what is P1x, can you please tell me what it is? What does that mean? It means the active power flowing in the lines connected to node 1. So out of node 1, there are lots of lines originating from node 1. That's the network. Yeah, P1x is sum of all those power that are flowing out of the lines from node 1. Right? What is Pg1? Pg1 is the power a generator is injecting into it. What is PD1? This is Pg1. What is PD1? PD1 is the power that a load is consuming. That is connected to generator 1. That is connected to node 1. Okay? So you have the first equation relating to node 1, right? So where do I get P1x? Well, P1x, you have the equation. You don't have to memorize, it's there. And it's got to do with the network lines, the admittances of the lines and, all the lines that are connecting to node 1, the network. Yeah? Okay? So in that, you can see voltage magnitudes appear. Voltage magnitudes of the various bus bars appear, which are unknowns, right? The voltage angles appear, because theta ik is theta I minus theta k. So the unknowns appear there. Yeah? Unknowns appear in the power equations of the power that is flowing on the lines, right? Okay? So now we look at this. So for every single node, we can write these power balance equations, right? For generator, we only have active power balance, but for load buses, we have active power balance and reactive power balance equation, right? Which is in the form of Fx equal to 0. So on the right, then we stack all the unknown variables. We stack all the unknown variables, right? So we have node 1 to node n equations, right? Node 1 to node n equations for each node. We know for it's very important, I've said this a number of times, for load buses you are going to write 2 equations, for generator buses you're going to write 1 equation, right? So, but for generator bus you have 1 less unknown, only the voltage angle. So you list all the unknowns. So you list the thetas, voltage angles which you don't know for all the buses, right? Theta 1 to theta n, right? You also list all the voltages, voltage magnitudes, which are unknowns. But of course, if it's a known voltage, you don't put it there. Only the unknown voltages, right? So you arrange it in this way. Now, this arrangement is important because how you arrange this unknown variables and how you write the equations F1 to Fn will then determine what the Jacobian matrix is going to be, which you will see shortly. Now, the Jacobian matrix, provided that I have organized my unknown variables like theta 1, theta 2 up to theta n, magnitude V1 up to magnitude Vn, provided that I've organized it like that, you can see on the right, I've highlighted in yellow, right? If you organize it in that, and your functions are F1 organized as F1 to F2n, if you have organized it that way, right? And you know what is function F1, what is function F2, and so on. Then the 1 element is dF1, d theta 1. Why? The first function is F1, right? Because imagine my first function is F1. If I organize my functions like F1, F2, F3, etc., first function is F1. So the 1 element is dF1, d theta 1. Because why? Because this element here is theta 1. df1 d theta 1, then can multiply with theta 1, right? Then the next 1, 2 element would be what? df1 d theta 2, because then that can be multiplied by theta 2, right? And so on. So the second row then will be 2, 1 element will be df2 d theta 1. 2, 2 element will be df2 d theta 2. And that has to do with the way I have organized my functions and unknown variables. Okay? Because there is an example, you will see this as well. And then the equations for Newton-Raphson, we talked about it. Delta x must be inverse of the Jacobian evaluated at the our current guess, multiplied by minus f evaluated at our current guess, and delta x is our current guess plus the current guess plus delta. A new refined guess, refined answer is our current answer plus delta x. So once you compute delta x, we can refine the answer we got, and we can stop the iterative process when the solution that we obtain, when we plug it into the function f doesn't change. In other words, function f is near enough to 0. Because the actual answer, if the answer is the correct answer, when you plug it into the function, it must be 0, right? Fx, if fx equal to 0, so if the answer for x is the actual answer, right, it will evaluate to 0. So some things for you to know, like if you understood what I said, then you will know the dimension of the unknown variables will be 2n, n being the number of nodes, right? Minus 2 minus m, where m is the number of generator buses. So does that make sense to you? Why is 2n minus 2 minus m? If you have n nodes, well, 2 times n is, well, imagine each of the nodes, you're going to write 2n equations, right? Each of the nodes, you're going to write 2 equations. So if you have n nodes, well, you have 2n. However, you subtract 2, because slack bus, you know the voltage magnitude and voltage angle. So you subtract 2 for that. Then, if there are m generator buses, right, you don't have to write 2 equations, you only write 1 equation. So we subtract m as well, right? Okay. So then dimension of the function vector, again, the dimension of the unknown vector and dimension of the function vector is the same, right? And a dimension of the Jacobian matrix, well, then it's 2n minus 2 minus m times 2n minus 2 minus m, right? It's the dimension of the unknown variable. Is a square matrix times the dimension of the unknown variable. Okay. So here is a simple example where we are looking at 2 buses, a swing bus and a load bus. So for the swing bus, we only know the voltage magnitude and the angle. The load bus, we know the loads, P load and Q load. We know that, right? So we we want to find the voltage angle and the voltage magnitude at bus 2. So that's the unknown, right? The unknown vector is going to be that. Okay? So so this is the unknown vector, as I said here. V theta 2 and V2, here is theta 2 and V2, that's the unknown vector. We need to know the function vector. Function vector is f. What is the function vector? Function vector is all the power that is flowing, has to do with the power flowing in the network through all the lines connected to node 2, right? P2x and Q2x. So we need to know P2X and Q2X, right? So those are the active power and reactive power flowing in the lines connected to node 2. We need to relate that to what's consumed by the load. That's the power balance, right? So we need to write those two equations. There is no generator connected, so PG2 has to be 0. QG2 has to be 0 because there is no generator. There is a load connected to 2, so PD2 is 2, QD2 is 1, right? We know that. They are constant values. So now we know that we need the expressions for P2X and Q2X. There is a formula sheet, right? We know what that means. They are the power flows, active power and reactive power flows in the lines in the network. We know that. But we haven't memorized the equations for that. We don't have to. We know there is a formula. So we're going to use the formula. So P2X, if you use the formula, right, and Q2X. So let's have a look at the formula. The formula that you will get is this, isn't it? PIX, QIX. That's the formula you're going to get. So we need to know P2X and Q2X, right? So what is P2X? So I need to substitute I equal to 2. It's pretty straightforward. K going from 1 to n. What is n? The number of nodes in the network. How many nodes are there? There's only 2 nodes, right? K equal to 1 to 2, right? Okay. So I is 2. So magnitude V2, right? I is 2, right? Magnitude Vk, K fine. K is a dummy variable that changes from 1 to 2, right? Okay. So Vi is V2, Vk is fine because K is a dummy variable. Yeah, it's changing from that to that. Okay, cos theta Ik, that's no problem. That's part of our unknown vector, right? So I there is 1, right? I there is 1. K is a dummy vector, dummy variable. Sin theta Ik, I is 1. K is a dummy variable. G I is 1, so G I 1K, B 1K, right? K is dummy variable, I is 1, right? So what is GIK and BIK? Well, that has to do with the network. That's got to do with the Y-bus matrix, right? That's got to do with the Y-bus matrix. So we'll come back to that, right? So what I'm trying to say is P1x and P2x and Q2x you can write, because if you are given this formula, which is, and if you substitute, as I said, well, this is a substitution, right? So we have a summation. Summation has 2 terms, right? Because a little n is 2, so it has 2 terms. So those are the 2 expressions that you will get if you write it. So we just need to know what is G21, G22, G21, G22. We need to know B21 and also B22, right? We need to know that. So what are they? This is where this becomes important, the Y-bus matrix, right? Those have got to do with the elements of the Y-bus matrix. What is the Y-bus matrix? Because this is only two nodes. So we're going to have Y11 uppercase, right? Y12, Y21, and Y22, right? We're going to have those, right? So the 1 element, so this will be G11 plus JB11, because that's admittance, which has a conductance and a susceptance. So that's Y11. Y12 would be G12 plus JB12. So in this equation, you know what these things are. Sorry, not that. You know what these things are. These parameters, you know what they are and where to get them, right? You have to write the Y-bus matrix. Once you write the Y-bus matrix, you look at the elements of the Y-bus matrix to actually find what those G and B values are. So what I'm trying to tell you is that we have, by writing the power balance equations, we've got these two equations. Right? We have those two equations. We have those two equations. These are the power balance equations, because a power balance equation is this: P2x minus Pg2 plus Pd2 must equal 0, Q2x. We've got that. We've got that equation. So you need to, I have explained to you, I have told you, you may not need to memorize the formulas for the power flows, the active power, reactive power, but you need to understand what's going on, so you can do these calculations and it makes sense. Okay? So we have the equations. All right. So this is what I'm trying to say now. So we have the first equation is F1, F2 must equal, well, Fx is that. You have two equations, F1 and F2. F1 is P2x minus Pg2 plus Pd2. We know Pg2, which is a constant. We know Pd2, which is a constant. P2x, we know, we've written that. Same can be said about the second equations, F2, we can. Now, we know that the unknown variable, unknown vector is theta2 and v2. So I can write the Jacobian matrix now. Jacobian matrix is going to be what? df1 d theta 2, because this is theta 2. And df1 dv2, because that's v2. And then df2 d theta 2, df2 dv2. That's the Jacobian matrix. Because we need the Jacobian matrix to compute delta x in our iteration. Because df1 d theta 1, which is this term, gets multiplied by theta 2. Right? When we multiply by the Jacobian by the unknown vector, df1 d theta 2 gets multiplied by theta 2. df1 dv2 gets multiplied by v2. That's how I structure the Jacobian matrix. Yeah. So we know what f1 is, so we can compute df1 d theta 2. You can just differentiate. Right? If you know that, you can find that. If you know f2, you can find that. Right? So all the elements in the Jacobian matrix we can compute. We can compute. So the Jacobian matrix is going to be that. Right? I'm not going to differentiate because you know how to differentiate. That's the Jacobian matrix. Okay? They are in terms of the unknown parameters, unknown variables that we are trying to determine. They are in terms of theta 2, it's in terms of magnitude v2, right? Yeah. So delta x can then be computed by evaluating the Jacobian matrix with the current values we have for those unknowns, right? And then we can evaluate the function with the current values we know for the unknowns, right? Compute delta x and we can refine that answer. We can refine that answer. And that's what that is all about. Just showing you the numbers, which I'm not going to go through, right? I've talked about the method. I hope you understood that, what I said. You can follow the steps and the answers are there. Make sure you do that and you're comfortable with this example. That's a simple example we're talking about. And once you know the voltage, magnitude and angle at that bus, once you know the voltage, magnitude and angle at this bus, right? You know the impedance of this line or admittance of that line, you can calculate the current. Right? You can calculate the current. And if you know the current, then power flowing out of this node can be calculated, power flowing into this node can be calculated. It should be these values, and then the difference in the powers originating from node 1 minus what is arriving at node 2 must be the loss in the line. So you can, once you know the voltage magnitude at each node, you can calculate everything else. You can calculate everything else. Right? That's why in this method, we're trying to calculate the voltage magnitudes and angles at every node. So let's go through, we can go through another example. This is this is a 3-bus system. The method is still the same, right? Method is still the same. So I'm just going to highlight some important points. I'm not going to differentiate. I'm not going to multiply numbers because you know how to do that. I'm not going to show that. I want you to understand the process, the methods, and then for you to do the questions yourself. So we have a swing bus, so voltage magnitude and angle is known. We have a load bus, so P and Q are given. So there will be 2 unknown variables here, V2 and theta 2. Here, this is a generator bus. So voltage magnitude is known, P is known. Unknown there is theta 3, the voltage angle, right? So we need to write 3 equations because there's 3 unknowns. Theta 2 is unknown. This theta 3 is unknown, which is that guy. And V2 is also not known. So here we have I've organized the variables, not all thetas together and then V's together. It is not necessary. You can organize it in whichever way you want as long as you're consistent when you write the Jacobian matrix. Right? You can organize the unknowns in any way you want, but your Jacobian has to be consistent with the way you organize the unknown variables. So the functions are, again, of course, not only the unknown variables, also with the functions as well. Functions, I'm going to organize F1, F2, F3. What is F1? F1 is active power balance for bus 2, right? Active power balance for bus 2. What is F2? F2 is the active power balance for bus. Reactive power balance for bus 2 is F2, is the reactive power balance, right? And what is F3? F3 is the active power balance for bus 3. Right? I can organize it like that. Yeah? Okay? So, those power balance equations you know how to do. We need to know the powers which are flowing on the lines to the buses. Right? So, F1 is, P2, it's got to do with the active power balance on bus 2, so it's P2 minus PG2 plus PD2 must equal 0. Look at the formula, right? Reactive power balance at bus 2 is Q2 minus QG2 plus QD2 must equal 0. So P2 is the powers that are flowing on the lines. Q2 is the reactive power that are flowing on the lines. PG2, PD2 are constants. QG2, QD2 are constants, right? They are what the generators and the loads are supplying and consuming. And then the third one is related to bus 3, right? So I is equal to 3 for that equation, yeah, P3. And then you can write, and the Jacobian matrix, because we have organized our unknown vector as theta 2, magnitude V2 and theta 3, we organize it like this. The first element of the Jacobian matrix has to be dF1 d theta 2 related to that. Yeah? And then the next one dF1 magnitude V2, dF1 magnitude dF1 d theta 3. Yeah? And the rest of the calculations are now the same. That's it. The calculations are the same as I explained for the previous example. No difference. Okay? Is it all good? Yeah, makes sense? Okay, the rest of the calculations are the same. It's just a matter of you now calculating. just going through the answers. So I now want to tell, when you have a bigger network, doing these calculations is going to be tough, right? I mean, the electrical network is not going to have 3 buses. It's not going to have 2 buses as a simple example we talked about. It's not going to have 3 buses that we looked at there, which is, it's not going to be like that. And it's going to have number of buses. And how are we going to do this? We can write a program to do this. You can write a program, but somebody else has written a program and put it in this link, right? But you can write the program yourself as well, based on the theory that I talked about. But simply because there is a program that is available for us, doesn't mean we don't understand the methods of calculating. I've told you the methods, you understand the methods, and you will be tested on that. But obviously when you're tested, you will be tested on simple examples that can be done. But if you're an engineer and you understood, not if you are an engineer, if you understood what I've explained, the methods, you can write this program also. Of course, it's not going to be easy to write the program because you're generalizing things, but it can be done. All the theory that you need to write the program yourself, you already know. But on this website, this program somebody's written, some researchers, right? They've written, you need to download that because you need that to do your assignment, right? Because you have an assignment. And to do that assignment, you need to download that. And this is a toolbox written for MATLAB. So you need to use MATLAB if you're going to use this. So load flow can not only be done using this toolbox, using MATLAB, there are other packages that can be used, like Power Factory, like I think Western Power uses Power Factory. There are various other packages that can be used. Yeah. But the fundamental remain the same. There is a slack bus, there are some generator buses, there are some load buses, there is a bus admittance matrix, and so on, right? So I'm going to tell a little bit about it because there are some other if you go to that website, you can download the M files, which you have to do, and there are some other other documents that you can download to read how to use it, but using it is pretty simple. So this is what you call IEEE 9-bus system. So it's 9 buses, right, to do a load flow. There are 3 generators on this bus, on this network. The 3 generators are there, and there, connected to bus node 1, node 2, node 3. This is node 1, this is node 2, node 3. There are 9 nodes here, so that's why it's a 9-bus. It's an IEEE 9-bus. Why it's an IEEE? Well, IEEE published this as one of the test cases. The line data are presented here. So that's the series impedance. These are on the pi model, pi network, you have 2 capacitors on either side. So the admittances are given, right? So this is a standard network. So how do we use the program? Well, for the program to run, you need to give that information that is on this figure, right? You need to give program can't generate the answers without you giving the required inputs, right? You can't. So the program, you need to give the inputs. And how do you give the required inputs? You create an M file, right? You create a .m file, and then you need to load that into MATLAB. It's pretty straightforward, I'll tell you. So here, let's look at what the M file contains. So take a look at, so this is a matrix, right? In MATLAB, you can generate matrix. So this matrix, you need to call this variable, right? mpc.bus, something like that. Yeah, you give it a name to this matrix. The first column has to be the nodes. So there are 9 nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? The second column tells you the type. So this is the number of nodes that are there. Second one is the type. So there are 3 types. So if the type is 1, it's a PQ bus. If the type is 2, it's a PV bus. If the type is 3, it's a string bus. Because each of the node, you got to tell the program, is it a slack bus? Is it a generator bus? Or is it a load bus? Well, if you are doing the question by yourself, you need to know, isn't it? You need to know if it's a slack bus, what is a slack bus, what is a generator bus, what is a load bus. So you have the node identification number in the first column. Second column, you have the bus type. Okay. In the third column, you have whether that node is actually drawing any power. So node 1 doesn't draw any power. No active power, reactive power. No active power, reactive power, node 2. No active power, reactive power in node 3. Because remember, 3 generators were connected into these. So these are the 3 generators. There are no loads connected to that. So there's no external load connected to that. So that's why these numbers here are all 0. Okay. And if you look, the only nodes that are drawing power is node 5, node 6, and node 8. There are other nodes, but nothing is connected to those. So take a look. Node 5, we have that. Node 6, we have that. Right? What else? And node 8, we have that. Yeah? So 1, 2, 3. Yeah? So you put the active power and the reactive power, the relevant active power and reactive power there. Because all the other nodes, take for example node 4, right? Node 4 is a 0 and a 0. Let's have a look at node 4. Where is node 4? Node 4 is this. See, there is no load connected to node 4. Only the lines, network lines are connected. So there is no, yeah. So even if you're going to be using this program, right, and you know the network looks like this, you need to generate the input file. At least now you know how to generating the input file makes sense to you. Because look at node 4. Node 4, there is no load connected to that. So PD and QD is going to be 0. Right? So you got to have that understanding that I talked about so far in this lecture, even to use the program. Otherwise, what are you doing? Okay? You're not clicking a button, right? It's more than that. So then there are other parameters that you need to enter. And those parameters are, right, we don't worry too much about that, but you can read the documentation because documentation tells what is required, but I don't worry about any of that. And these ones here, that tells you the base kilovolts, the base voltage for each of the nodes, because remember everything is in per units. So it's fine, we do the calculation in per units, but if you want to know the exact values, then you need to know the base values to be able to find the exact values. So this column is there, but we won't be using it that much. But okay, so this is about bus data. This is about generator data. So it's only 3. We call this mpc.gen. Again, another variable in in the M file, right? So you can see here, there is only 3 nodes, or 3 buses where the generators are connected, bus 1, bus 2, bus number 3. The PG we need to write, right? Now notice that the second one 183 and 85. So let's have a look. Second one 183 and then 85, correct? Yeah, we taken it. The first bus is a slack bus. We don't know how much P, so the way it's been done is to say, well, that's 0. It's been put as 0 because it's a slack bus. It will provide whatever it has. It's going to be producing 0, but it's a slack bus, so you just put 0. We don't know the number. Because you don't know the number, you just put 0. I mean, that's how the program understands that. Program doesn't think it's going to give 0, but it understands. Because it's a slack bus, it will generate whatever it needs to generate. And then generator buses, we know the voltage magnitude. So we specify those. Yeah, generator buses, we know the voltage magnitudes. We specify them. Because generator 1 is a slack bus, it will know that's the voltage angle is 0 there. It knows that. Program knows that. And then, well, that's about generators. Then we need to talk about branch data, right? Branch data. So we have branches going from node 1 to node 4, 4 to 6, 6 to 9, 3 to 9, 9 to 8, 8 to 7, 7 to 2, 7 to 5, 5 to 4. If you look at the figure, we have all those branches. So we need to specify all those branches because otherwise the program won't know the network topology. Yeah, it needs to know. Then for the branch that is going from node 1 to node 4, there is no resistance. In the series part, there is no resistance. There is some reactance in the series branch. And there is no B, there is no capacitors hanging off the edge of the, it's not a pi model. It's just a series only. Series element, resistance and reactance only. It's not a pi, yeah, because there's various models. So if I look at one branch that goes from 4 to 6, there is some resistance, some reactance on the series branch, and then there are some resistors hanging off the end of each line. So it's a pi model, right? So we have the reactances, the admittances, the value for the capacitors, right? The two capacitors on either side. So here we have now given the branch data. So we are giving the program the network topology because we're telling how the lines are connected. We've told what the generators are. We told them, which nodes they are connected to, the voltage magnitudes. We talked about the loads which are connected to various nodes in this, right? So we've got all the inputs that the program needs to calculate, do the load flow. So how do we do this now? You have now downloaded the package in MATLAB. You have created this M file in some directory, right? Then you run this command. You load that the M file that you created. Let's call it IEEE case9.m. You can call it whatever, right? And then what you do is in MATLAB you load this case. Load case, file name, and then that's it. The program now got all the information it needs. So now you can ask the program to give you the answers you want. You can tell me, okay, tell me the Y matrix, the Y bus for this thing. I'll give you the Y bus matrix because it already knows all the detail. You can set the options. You can say, I want to use Newton-Raphson in the calculation. Or you can say, I want to do Gauss-Seidel. That's the method I want to use to do load flow calculations, right? And then you can say, okay, run power flow, run PF power flow with because MPF is the case file that we have created, right? We can run the load flow using either Newton-Raphson or Gauss-Seidel. Right? You can run it. And then when you run it, it's going to give you this output. Okay, so let's interpret this output. So notice for bus 1, 2, 3, 4, 5, then it's going to tell me all the voltage magnitudes, all the voltage angles, all the voltage magnitudes, all the voltage angles. It's going to output. Okay, it's going to tell me, well, this is the generator data. It's going to tell me how much generator 1 is producing, how much active power, because that's a slack bus. Generator 2 and 3, 163 and 85, they were the values we specified. It's going to tell how much reactive power each of the generators are going to produce. It's going to tell me how much each of the loads are going to consume. All the data is given. It outputs all that. So if we sum all the loads, we're going to get 315. If we sum all the generation, we're going to get 319. Then where is the rest? The rest will be the line losses. Right? And also I can tell, like here, right? So things that I've covered in red, I think this should be, there's a small mistake here. This should be a red. Yeah, this is a red. No, hang on a second. Voltage magnitude and angle are known. Okay. Yeah, that's correct. Everything is correct here. There is no mistake. So have a look. The ones that I put it in red, yeah.
How's the generator on bus 3 generating negative reactive power?
It can. Generator can generate negative reactive power or positive reactive power.
Does that mean it's drawing?
Yeah. No, it's because if the Q is positive, that means it's a consumption, right? Yeah, consumption. Q is negative, means it's generating. Sorry. No, it's the other way around. Yeah, It's actually so Q positive means it's supplying, right? Generator. It's for a generator. If Q positive means it's supplying, that's the sign convention. This Q negative means that particular generator will be consuming. Yeah, for generator. But for a load, if Q is positive, it's consuming. It's the other way around. Right?
So generator can consume power?
Yeah, generator can consume. Can consume reactive power. If the generator consumes active power, it's not a generator, it's a motor. That means it's operating in the motoring mode. So here I put the things in the in red and blue. So red means like for the first one, right? For the first generator, we know the voltage magnitude, we know the voltage angle. That's a slack bus, but we don't know P and Q. We determine that. Yeah. So this is specified value. This is the calculated values. So again, for generator 2, we know P. Oops. We know P, and also we know the voltage magnitude. We know P and the voltage magnitude. So what are we going to calculate? For that particular bus, we're calculating voltage angle and Q. Right? And so on. This is 4 parameters of interest. Here we have found all the 4 parameters. So the load flow program has given us the answers. Right? Given us the answers. So this is what it will generate. And also it will generate this. This will tell from bus 1 to bus 4. How much active power is flowing out of bus 1 and how much active power is flowing into bus 1. Right? And the difference in those two is the loss. Obviously, what flows out of bus 1 also flows into bus 4. What can you conclude? What can you conclude? Zero power loss on the line. That means that must be just an inductance there, no resistance, right? So you can see you can determine the losses on each of the lines, and you can sum all of them to find the total losses, and so on. All the answers are there. All the power flows on each of the lines. So now you know which program that you need to use to do your first assignment. First assignment is doing a load flow. And to be able to do a load flow, you have to create the case file with the correct inputs, put that in, run it, use Gauss-Seidel, use Newton-Raphson, get the answers, see if it all makes sense. But before doing all that, understand Gauss-Seidel, Newton-Raphson, make sure you can do those simple calculations because you will be tested on that, right? Understand the bus classifications and the load flow problem entirely, okay? So that brings us to the end of this chapter. I think this chapter is a very important chapter, which you need to know, right? And then when we do the subsequent chapters, understandings of this we will use. So it's a good time for you to do the assignment as well. So just make sure you fully grasp the technical concepts. You are able to do simple calculations manually, and then you download the program and do more complex load flows using the program, and you are able to do that. You are able to create the required input file to be able to get the answers you want. All right, so before we start our next chapter, which is chapter 5 on symmetrical faults, which will also require this understanding of load flow, which I hope you will master before that lecture. Now, before we go on to that lecture, we want to present to you another important topic or understanding on electrical safety. Because if you're working in a utility and you're working as an electrical engineer, you need to be fully aware of electrical safety. And to present that lecture on electrical safety, I brought along a practicing engineer who has worked in the industry for a long period of time, and Craig Hoskins. He's also a member of Engineers Australia Electrical Working Group. Is it electrical committee, electrical engineering college committee for Engineers Australia. So, Craig, I'll pass it to you to present these lectures on electrical safety. Yeah. Okay, so what we'll do is we'll take a 10-minute break, and when we come, Craig will present his lecture on electrical safety. Okay. You on the yeah.
By hand, how many buses can we do? 3?
Yeah.
Max?
2, 3. 3. Let's say 3.
Yeah. So nothing more than that in an exam.
Yeah. 3. Have a look at the past as well. Well, yeah, I think it's just to check the understanding. You know? It's not to waste your time on it. Exact. Not to do that. Yeah.
Number 1. Oh, okay. So they're actually on the, go to the slide. Where is it? Go to view. Yeah, and just go back to the slide because I was working on the notes. See it? Yep. And that can just. Yeah, that's okay. That's fine. So how will it pick up the?
It will be from the microphone.
That's right. But in terms of the recording,
It's already recorded.
it's recorded from what as it goes up there.
Yeah.
Right.
Like that.
Right. Yep. That's fine.
Not this screen. This screen has
Yeah. Yep.
another 5
Yeah.
seconds.
Yep. Yep. So where's all the coffee?
Drink coffee.
Oh. I thought you'd need a coffee by now.
We used to.
Oh dear. We used to.
How much coffee did you consume?
Well, when we had 4 lectures straight in the morning, we'd. I can remember in first year we went from physics and things. We actually disappeared into the read library. Had grabbed a coffee between the 15 minutes between the next lecture because they used to always be 45.
You graduated from which grade year? How many years ago? Long time ago?
Yeah, my final year was 81.
Okay. So I think maybe you can do a self-introduction and stuff.
Yep, no, I've actually got a little bit in there. Yep. Okay, well, let's get started. So, thanks Tyrone for inviting me to present a couple of lectures on electrical safety. This is actually quite important. It's something you're not actually getting tested on, but it's very important when you actually get into the workforce. As electrical engineers, you've got to deal with electricity, and electricity can be dangerous. So let's start. Okay, so just some disclaimers. We've got to be very careful these days. But basically, the presentation is only intended to increase your safety awareness of typical electrical hazards you might encounter in the workplace. It's not a university safety course, and it doesn't give you any authorization to go and work on or near electrical equipment or installations. It's only of a general nature and shouldn't be relied upon to ensure your personal safety around electrical hazards. As I said, awareness of electrical hazards is only the first step in your journey to work safely around electricity in your future jobs. And when you are employed, you'll be required to actually follow all your future employers' safety procedures requirements, which could include specific electrical safety training. So this is just an awareness. Sorry, yep?
What if an employer is inept and they don't have such safety procedures?
Well, you might have to actually implement them. So that's the sort of thing. I mean, compared to when I first came out, 30, 40 years ago, there's a lot more regulation around safety than there was then. So anyway, we'll talk about that as we go along. So the contents really are going to be about your personal electrical safety awareness. So we'll go through, talk a little bit about my background. Why is electricity dangerous? And the fact is that electrical engineers can be exposed to electrical hazards. Yep.
Sorry, it says sharing is paused when you share with
I don't know what that is. What does that mean? I'll get my technical expert. Your shared window to the front.
For anyone watching online or anything, I think you need to reshare this with.
Yeah. Let's stop and share.
I mean, yeah. It's being recorded anyway, so you can have a quick look at it. Someone can have a quick look at it later on anyway. That's doing it. A green screen share. Yep. So we're going to talk about electric shock and electrocution. And go through those sort of things. And then in lecture 2, we'll look more about what they call arcing faults and arc flash hazards. So we're going to start with the first thing you think of, which is getting an electric shock. So we'll move on from there. Come here. So who am I? So I'm an electrical engineering graduate. I graduated in '82, which is the year I started work, and a member of the the Engineers Australia WA Electrical College panel. That's just a committee that looks at providing the lectures and things that electrical engineers go to. So I guess for the last 20 years I've worked on wind turbines, wind diesel systems, gas turbines, from what was Western Power to Synergy, sort of various name changes. So that's, sorry? No, that's a wind turbine, sort of right up the top. That's actually over in South Australia. So that's part of the fun part of being an electrical engineer. So the sort of projects I've worked on, you might be familiar with the Albany Wind Farm. So I was involved with that. This is back in 2000. So our group basically got the wind farm put together. I spent a fair bit of time looking at the cabling and transformers and things. If you go down to Hopetown is off the grid. It actually has its own wind diesel power station with a couple of wind turbines. So also Coral Bay, we've put wind turbines up there which are actually cyclone rated, and a power station. So in a sense, these remote power stations, they're isolated, so they're like what they call, you call them now a microgrid, and they really have everything in terms of electrical engineering that you have to deal with. So that's sort of where I guess I've got some experience of a small system, but you actually have to deal with all the things you have to do on a big grid, but in a smaller sort of scale. The last sort of 10 years I've played around with gas turbines. This is one of the more advanced gas turbines down at Kwinana Power Station. And that's been mainly looking at faults, looking at their control system a bit to sort of see what's sort of happening. And also you get the chance when you're involved in power generation, you get the chance when they have their overhauls of actually seeing what's actually in them. So this is actually a combined cycle gas turbine rotor down at, again, Kwinana. It's called Coburn. So you get to see all the mechanical bits as well as the electrical bits. So electricity is essential in our modern society. The three important things, obviously, are coffee, Netflix, and electric cars. But it is dangerous if not contained and controlled. So this is really sort of saying, you can touch something, you'll get electrocuted. Things can blow up. So that's it. It's essential, but it's dangerous, like most things. So if we look at the number of electrical deaths in 2019-20, this is across Australia and New Zealand. So they actually, you can see here that in our case, WH had 2 deaths. But if you look at the general sort of the way they've grouped them, here sort of about half of the deaths were to do with distribution networks. So this is where, as I say, 5 of the deaths were associated with overhead conductors. So that's the case of where you have, the classic one is cranes putting up a jib and someone inside being electrocuted. But also things happen in customers' installations. So I actually went and had a look at where those 2 deaths occurred in WA. And the 2 recorded deaths, one person was electrocuted from touching the live heating and pumping equipment of his home spa. So this is up in Joondalup, the year before last, or last year. And another person was electrocuted from contact with wiring in something he'd made what they call an electrical wood fractal burner. So that's where they actually sort of do things with the wood and actually put a high voltage on them. So someone had done a DIY thing and actually had killed themselves. So these 2 people had killed themselves by touching electricity. And as an electrical engineer, you sort of want to know, well, what happened? I mean, electrical engineers are the only ones who are really going to try and understand how things happened and what, how you'd prevent it. So what makes electricity dangerous? Well, it's basically that household voltages, the things we take for granted, these power points, 240 volts can kill. And we've got so used to it. And only a relatively low current, only 100 milliamps. So that's my old phone charger. That was 100 milliamps. That's sort of, we're looking about phone charger stuff in terms of the AC voltage or the AC current that they actually absorb. So it's not very much. And the key thing is with electricity, it's usually invisible and silent. We cannot easily distinguish between a live circuit and something that's de-energized just using our physical senses. And that's what's so dangerous. The world around us has been worked out by electrical engineers to make things safe. So, the wires behind a power point are dangerous, but the way it's been done with plastic and things, you touch it, you're safe. So the world around us has been made safe. But as an electrical engineer, you start to go behind the boards. Yep.
So would you say that it's the current or voltage that kills the person?
That's what we're going to deal with, yes. So we'll see that in a minute. So we've got this issue that you look at the switchboard, you open it up, and it doesn't sort of say I'm live, I'm dangerous. It doesn't shout I'm dangerous. It's a silent killer. But in larger, rather than usually your domestic home or something like that, in larger installations with higher fault levels, we can also get what they call arc flash explosions. So you can actually get these, which are very, very dangerous. You may not be electrocuted, but you'll be fried. So it's a different sort of issue. So okay, so where could you be working in the future? Well, it's obviously around about electricity. So you could be somewhere. You could be to do with the power station. A power station somewhere. So that could be Synergy, Alinta, Fortescue, BHP. You could also work in the transmission systems. So that's obviously usually Western Power, Horizon Power, or the distribution systems. And again, Western Power, Horizon Power. But a lot of engineers work in with industrial customers. So they're refineries, mines, manufacturers. Again, Alcoa's, Woodside, Petroleum, BHP, Rio. Other people actually engineers work directly in with commercial buildings, with shopping centres and hospitals. For instance, most hospitals have an electrical engineer on staff. But also you'll get the energy consultants. So you'll get the GHDs, the Hatches, the Jacobs, and other people who actually deal with are consulting engineers. So they're the sort of areas that electrical power engineers, will actually be employed. So let's have a look at what do electrical engineers sort of do. So I've really sort of separated this into 4 sections, and this is to do with there's electricity regulation. So WA has electricity regulations which relates to who can and can't do electrical work. So it's sort of an example of saying, okay, well let's start with here. Okay, electrical design. Usually complex LV and HV design is done by engineers. Where you have some standard designs, electricians get involved with them all the time. That they've told there's a 30 amp circuit breaker, what cable do I use? They'll know that. And that's something that electrical engineers, you may not have actually done it in your course yet, but the first thing I got when I first graduated and went to work for Alcoa was they handed me an AS3000 wiring rules book, which I'd never seen before. And it's something that you guys, when you're sort of looking at being employed, I mean, that might be something that someone will ask you, an employer will ask you before you even, one of the questions, do you know about the Australian wiring rules? So again, that's something, in our day, there wasn't a way of actually getting information as readily as it is today. So, what I want you to like you to do is just go and have a look at some things. A bit later on, we'll sort of show you a few good booklets and things that it's worthwhile going and have a look at it. I mean, when you go for an interview, you know, what are people going to ask you? You know, what are, even before you get a job, people aren't just going to actually come along and say, oh, you're an electrical engineer from UWA, here's a job. You'll be competing with a whole lot of other people from different universities. The question is, how do you prepare for that? That's something that we'll sort of talk about. So basically, yes, electrical design, that's usually that's where engineers tend to be. Now, in the licensing rules, so these are the WA licensing rules, and again, you'll be able to find them if you just Google it. You'll be able to find what they are. Everyone's allowed to work on low voltage equipment. So that's, you know, control gear, you know, 24 volt stuff, because there's limited danger with that. So what we can see here is, here's the voltage levels. 0 to 50 volts AC or 120 volts DC is extra low voltage. Low voltage is defined as up to 1,000 volts, and then high voltage is beyond that. So they're the voltage levels that you deal with. So here it can be controls, computers, you know, 24 volt stuff. No one's worried about, you know, you playing around with that. So electrical engineers and electricians can do that. Now, when it comes to, we'll just go to the end one, which is electrical work. Electricians are the only ones who are allowed to work on electrical installations, machines and equipment. Now, that means installing it and doing things with it. But they have defined in the actual regulations, because there's always been an area where, you know, when people are commissioning plant, you've got electricians, you've got engineers all around there, and you tend to be doing things. So they've actually defined here that where you're is inspection, testing, commissioning, fault finding, in the law, by the law, electrical engineers, but they have to be professionally qualified power engineers with experience, you know, and they're people who work on commissioning and things. So as a graduate engineer, you're not going to be expected to go in there and do things, but you'll actually be next to someone. You'll be sort of following someone. But at some point, there is a legal recognition that electrical engineers do get involved with that work and can be, therefore, exposed to electrical hazards. So in practice, you know, it'll be you'll be trained and authorised by an employer to be able to do certain jobs. So that's sort of the law, but you can sort of see it's quite a good way of looking at, you know, the way people do things. But what we're going to do now is we're really going to concentrate on this area. This is the area where electrical engineers get exposed to electrical issues, electrical hazards. So what might you be doing? Well, here's an example. Quite often things are in switchboards. It can be 240 volts, reading, you know, this is a communications cabinet that's got 240 volts in there, looking at gear. This is actually an inverter drive. Well, it was an inverter drive, but it's used as a dump resistor, a variable dump load. And you can see here you've got the red, white, blue. This is three-phase. You'll also see there's things are exposed there, but there are you might not be able to see there. There's perspex and covers and things there. So again, you know, it looks pretty benign, but if it's actually online and you're trying to fault find, you know, things are actually live. So there's 240. When you start looking at, this is from the Albany Wind Farm. So this is the case of you've got 22 kV cables coming in here, which go out from the wind farm to the substation. And this is the classic. This is very similar to, this is a Western Power sort of design. So these are the actual LV cables. So there's red, white, blue, each one of those, and each one of those is a switch fuse carrier. So if you were in Western Power, you'd see a lot of that sort of stuff, that sort of gear. And you can also be in substations. So here we've got, this is actually a generator step-up transformer at Pinjar, which is north of Perth. And here we've got 132 kV. So there you are, you're standing there. At that point there, you've got 132,000 volts. Now, you're quite safe, but it's recognising that. So you sort of say, well, what's this got to do with me? What's the issue? Well, this is a very unfortunate story about a young graduate engineer from UWA. This is back in 2000. And he basically was with Western Power and on a rotation out in the country. So he was out at Kalgoorlie, and he was sort of learning the ropes with an electrician who was a technical officer. So this is a case where there was a substation, but it was an open substation, and there were a bit like this here. There were open bushings. It was protected by a fence, and it was locked. So it was ensuring the public wouldn't be in danger. But in his case, they had to come along and just check it. Now, there was a bit of vegetation in the compound. That was discussed. And I suspect that the technical officer, went around the corner or went to look at something else. But here, and there was a coroner's inquest into this. So there was a discussion about vegetation removal. Then, at some point, a little bit later than that, Darren made contact with, or was in sufficient proximity to 19,000 volt arcing horn, which is what that sort of thing there, received a large shock, which actually engulfed him in the fire. So he was taken by ambulance to Kalgoorlie. So he was still alive, and that's what happens. You receive a large shock, and you won't have heart fibrillations, a very large shock, but it will actually burn your organs and things. So he was taken to regional hospital and flown to Perth, but he died that evening. So this was, in a sense, a catalyst back in the mid-2000s that the Director of Energy Safety actually got with UWA and actually produced a number of, they were actually looking at energy safety for graduates, because things do happen. You can be trained, but you have to, electrical engineers need to have a sense of danger around electricity. It's silent, you have to get this, it takes a while, but you just have to be aware of, almost a slight, you've always got to be hesitant, so you don't just sort of go, oh, look at that switchboard, or look at that item, and bang, you get a zap. But this is sort of one of the reasons why we're doing it, because it can happen to engineers, not just other people, because we are exposed to the hazards. So, electrical safety at work, well, employers have a legal responsibility to provide a safe work environment, and this has become stronger and stronger over the period. So you're not going to be thrown to the wolves, but you have to be aware of this. They are actually required to provide you with training and supervision. But even with supervision, if you're in an area where there's something that's dangerous and you just happen to go and walk into it, well, you could be aware of it, but you've got to be very diligent. So the other thing is the electrical works regulated, as we saw there about the regulations, to maximise electrical safety for the general public and people working in the electrical industry. So what I'd recommend is, so here are a couple of things that are of interest. You'll see there's even a UWA found on the net, UWA electrical safety work procedures. So UWA has these things. But there's an excellent, if you just Google electrical safety manual, hopefully this would come up. This is actually from Whyalla, and it's actually quite a good, again, worthwhile downloading and have a bit of a look at it. See what the has anyone got a computer with internet? Why don't you see if you can actually find that one for us? Yeah, just put electrical safety manual. It should Google up to it. So this is a classic industrial safety manual. It's got lots of interesting stuff in it. Again, worthwhile just having a flick through to sort of see what sort of things sort of industry deal with. The other one here is this is the electrical system safety rules for Western Power. Again, it's online. Just grab a copy and have a look. In fact, I'm using quite a few of their little diagrams to sort of explain some things to you. And you've also got, this is the Department of Minerals, Mine Industry Regulation and Safety. So the actual energy safety part of this actually is in this department. And there's another, if you go looking for that one, you'll sort of go into that area. So again, you start getting familiar with, there's regulations and things. These are the things that in WA you have to actually abide by. Yep. So that came up there. Yeah, I think it was pretty, but it's actually really quite good. It's when, sorry. Yeah. But I mean, don't download it now. But do it at home and just have a flick through it because it gives you a real sense of what's about electrical safety because they're trying to cover a whole range of things from training to what the sort of things I'll be talking about today. So okay, now have you done risk management sort of in your system? You had covered any of that? Yeah. So the classic one is hazard risk management. So there's 4 steps to it. Identify the hazards, assess the risks, control the hazards, and check the controls. That's the classic. And that's from a WorkSafe document, but it's just the standard one. So what we're going to do is have a bit of a look at really identifying the hazards here. We're not going to look at assess the risks as much, but really just to give you some identification of hazards. So what is an electrical hazard? Well, here's a definition, and this is from OSHA in USA, which is like our WorkSafe. And the way they've defined it is electrical hazard is defined as a serious workplace hazard that exposes workers to the following: burns, electrocution, shock, arc flash, arc blast, fire, explosions. So they actually got it as be safe. That's the way they've done it. Now what I've done is you can look at the reddish ones are to do with the shock, arc flash is the yellow, and the thermal types are to do with Yep.
So not really related to like safety and all that, but in terms of your years of experience, what would you expect from a graduate engineer or like a project engineer, like who just joined a company in terms of
sorry, to when they join your company, what were you expecting?
What would you expect them to or like what would you expect them to be capable of?
Well, that's sort of something we're sort of talking about. I mean, the tricky thing is it's not until you actually start doing real problems that you think, oh, wait a sec, I did that back in second year, or you actually find that your education, you've actually done a lot of things, but the problem is until you actually see an example, sometimes you don't realise what you know. And that's what we're sort of talking about with like symmetrical faults and things like that. Well, from a practical point of view, what's it useful to know? I mean, you've done transformers, you've done machines. You have to go back to that because the sort of power, what you tend to find is you learn about things and you learn about how they model, then you start putting them all together, and that's where you start doing power systems analysis, because you actually have to use all that stuff but also protection is also where you use that. That there are higher levels in a sense than just the individual components. So, yeah, it's. I guess what we'd like to do is provide a few more sort of classic examples that get you ready for work, or things that, you know, again, you think about, well, if an employer, I go to an interview with an employer and they're going to ask me some basic electrical things to make sure that I'm not someone, you know, some fake person or someone who stole someone's identity. What sort of things would you expect them to sort of, you know, to ask you? And they won't be that complicated. They won't be solve a 3-bus, you know, using a Jacobian matrix or whatever. It won't be anything like that. But that's the sort of thing. The question is, what do you need to know? And you have to look at, I guess the first thing is looking at that diagram of an electrical network. You know, what's there? You know, there's generators, there's lines, there's transformers, there's loads, there's motors. They're all the things you think, oh, gee, I've done something about that. But it's sort of getting to the point where the practical side of it is, well, what's something I need to know? Well, the biggest thing you need to know is your electrical power engineers. One thing you need to know is power. You know, what is it? You know, power is equal to VI cos theta. That's a very standard thing. You need to know V equals IR. You know, those sort of things you'll use time and time again, and we'll actually show you a little bit here. So let's get into this. Electrical shocks can be serious. Here's a guy that was part of an experiment. Would you like to be this guy? And what they were looking at was at what point did he suffer pain? So this is actually quite a famous sort of thing. Other things with electrical shocks, you can get burns. The next size is you can actually, your heart goes and starts fibrillating, which means it basically flutters. It hasn't stopped, but it's fluttering. But the problem is, it's not actually pumping anything at all. So that's when you start using defibrillators. Let's have a look here. So this is a very generic sort of idea of what happens with electrical current going through the body. So usually less than a milliamp, you don't even sort of understand it. Up to 10 milliamps, you know, we're talking about milliamps, we're not talking about amps, we're talking about milliamps. You start getting a little bit of painful sensation. Around 10 milliamps, 10 to 15, if you're holding something in your hand, a cable, you won't be able to let it go because it's actually got your muscles. They've clamped on it, and that's a very dangerous thing. One thing you never do as an electrical engineer is you grab anything. You never grab anything. You know. Well, when you kit it up, that's fine. But you just have to think. You just have to think about, you know, being in a thing. You never grab something. You know, it's just that sort of, you know, issue. 30 milliamps, you start getting respiratory paralysis, you stop breathing. 75 to 100, you start getting fibrillation, and that's basically when the heart action it's fluttering. It's not actually going in its rhythm. Now, the interesting thing is, of course, a defibrillator actually gives you an electric shock, and a defibrillator actually gives you an electric shock and actually stops your heart on the basis that what happens is when the heart is stopped, it will actually, the whole your system, it's like a computer reboot. It actually reboots and your body starts the whole system again in its correct mode. So that was always interesting. You always think about people doing this, they're dead, they haven't got any heartbeat. Well, they've actually got a heartbeat. What you're actually doing is you're actually sort of not killing them, but you're actually stopping their heart. So it will actually naturally come back in its right rhythm. So there's a range there. When you get up into the amperage ranges, you can get heart paralysis. It'll just stop. You know, it'll actually stop beating. But you also get tissue burning. So, as you say, these are not big numbers. You know, when you start looking at even a small distribution board here, you might have 100 amps flowing through there. So, factors that affect the severity of the shock. Well, the first thing is the magnitude. We've sort of seen that. Oops, I'm not dropping this thing. The first thing is the magnitude. Now, this is where your guns at this, you know, I body equals V touch over R body. That sounds very familiar. So even Ohm's law applies to people. Now, there's some interesting things here. I've just taken a few values. Again, there's a standard which talks about effects of current on human beings. So you can see here, I've just sort of got a finger-to-finger sort of at 100 volts. And you can see these quite high resistances. But as you come down in terms of hand-to-hand at 100, you can see that you know, you're in the 1,000 ohms stuff. As you go up and higher in voltage, it actually comes lower. So that's part of the reason why 24 volts is pretty well, you know, won't usually kill you unless you're in salt water or doing something strange, because firstly your resistance is much higher. Now internally, if you exclude the skin, so the skin is really the skin has the highest resistance. Your internals don't have a great deal of resistance. They're more in the 500 to 1,000 ohms. So that gives you an idea. Yes, you can be lucky if you've got a low voltage and you've got dry hands and you don't have any cuts. That's why people, you know, might just happen to go, oh, you know, get a slight hit. But as soon as you start putting area, so it's the old area issue, that decreases the resistance, therefore increases the current. So there's the magnitude, there's the length of time, the current path. So in here, if the current path is close to the heart, that's where you start getting the risk of fibrillation. So if you're hand to hand, it's going to go across your heart. If it's hand to foot, again, it'll go through your heart. If it's foot to foot, it's much less going through your heart. So there's these sort of things. There's the frequency. The frequency of the current. DC is not as dangerous as AC. So we saw back then that the low voltage, the ultra low voltage was 50 volts AC and 100 whatever it was volts DC. That's sort of the reason that it's not as potent, but it's still, you know, you can still die from it, and obviously the individual's health and pathology. So here we go. This looks like something that you're used to, a nice little circuit. And this is Fred. So this is this is a model. So we all love models. Engineers love models. So here we go. Here's 240 volts. Fred's touching the active. I made sure it was the active. So the brown's active and blue's neutral. So the current flow. So basically what you've got is 240 volts, you've got a source and wire resistance. Now it'll go through your body. In this particular case, it'll actually split between your legs. So guess what? That's a parallel path. Remember those things? And then come back. So what you've got there is you've actually got, remember the skin is the most resistive part. So the soles of your feet and your hands. The rest internally won't be very much. So here we've got an issue where the current, you've got a driving voltage, the current obviously relates to the resistance. So if you can increase the resistance, you'll reduce the current. And that's where, for instance, you'll have, as an engineer, you'll have electrical insulating boots. So they're fairly standard. You'll get floor insulation. You might see people with mats, with electrical, you know, insulating mats. You can also be using gloves. So they all have an effect to reduce the impact of you actually getting electric shock. So yeah, okay, got old Ohm's law here. So what can happen here is, let's assume the resistance total is 2,000 ohms. So that's everything. 240 divided by 2,000 gives you 120 milliamps. So there you go. That's just showing you that just a simple thing with ohms, those sort of ohms that we sort of think are reasonable, just shows you what can happen. So that's what's called a direct contact fault. That's when you're actually touching a wire. But you can also get an indirect contact electrical shock. And this is basically where you've got some equipment with power, but what's happened is, an earth, what's happened is the chassis hasn't been earthed. So if you do actually get an insulation fault, you get a fault to the actual outside, that basically livens that up. So it's you know, you thought you were safe, but you're actually not. So this is the case of no earth cable connected to the metal cover, insulation fault, live current, and you get electric shock from touching the cover. Now, when you go and look at switchboards, you'll actually sort of see the switchboards have all got earth, you know, green and yellow earth cables. Everything's connected. You know, bus bar, everything, covers are always connected for that reason. And the reason is that. So there's that. Yeah, we'll go to the next one. So okay, electric shocks in the workplace. Okay, this is guess time. So what's number one? What do you think the electric shock hazard is?
Is the bus bar somehow connected to the rest of the
So look at the wires up there. You know, there's exposed. Things are exposed. So if you're actually in there, and that was live, of course you could accidentally touch one of those terminals. So it's a classic one. Okay, what about number two? Yep. So it's a cable the cable's got damaged. So that's sort of it. And number three is a good one. So that's really where you've got an actual electrical appliance that's actually there's some internal fault. Number four. Okay, so what's happened here is there's the earth bar, and in normal installations, your neutral is connected to the earth, and there's a reason for that. And that's to do with ensuring that if you actually get a fault coming back from via the earth cable, it will actually find its way back to the actual supply. So it actually, and therefore you'll actually trip your circuit breaker. And of course there's a overhead line. So again, a crane, anything that gets in proximity, you're in danger. And here, what do you think this one is? So it's actually wet, dampness. So for instance, the guy died up in Exmouth, I think yesterday or the day before when that cyclone went through, and he was trying to fix, there was a power pole, I think it was only LV, and he was trying to secure it, and he died because he obviously touched an electrical cable, or a live electrical part, but the worst thing was it was probably very wet. So dampness actually, you saw that in the resistance, dampness reduces your resistance, so you'll get a bigger shock. Okay, so getting into the industrial side of things, here we've got, again, the live conductors we talked about. You can have capacitors sitting there, and you don't realise them, and you go, whoop, bang. So normally they have discharge resistors and things like that, so you just have to be very careful. Now, something you've probably not seen before is current transformers. Have you done anything on current transformers at all? So a current transformer is basically, it's got a bus bar going through, which is like one turn, and you've got multiple turns. What that does is, if this is 100 amps and you've got 100 turns there, then you'll get 1 amp coming out there. The only issue, of course, is that that's in the amperage. But if those are open circuited, what happens is you've got 1 to 100. So this can actually become a very high voltage. So you might think you're on the secondary side. You're in a cabinet. It's not high voltage stuff, but you can create high voltages with CTs, and that's why they always get shorted when you have to actually maintain them. So let's have a look at controlling the hazards. Oops. So we've talked. Well, anyway, we've talked about them. I was going to get you to go through them. There's a few things. Obviously, the first thing that reduces the electrical hazard is if you isolate the supply. And therefore, there's no hazard. You know, you've taken the hazard away. You don't touch. You always test before touching, and that's very important. Avoid wet conditions. Wear corrective PPE. Check electrical equipment so there's no insulation fault. Things are properly earthed. That things are discharged. And there's barriers that also you have some residual current devices, some RCDs, earth fault protection where you can. So we'll look at high voltage hazards. Now in a substation, this is up at near Geraldton, this is actually a gas turbine substation, just a good picture. And you'll see there's a transformer. The actual generators are actually over here. So this is like 11 kV, sort of bus, open bus, and off it goes to the generators. So high voltage does the same thing to you. It can electrocute you, but it's got a couple of tricky things, which are sort of more relevant to high voltage. One is to do with close proximity to live conductors. The other one is induced voltage hazards, which you tend to get with HV. And the other thing is called step and touch voltage hazards, which tend to happen around substations and things. So, let's see if we can get this to go. So this is about proximity to a HV conductor. A good little video. What you can see is there that you don't actually have to touch a high voltage conductor to actually get a zap. So in this particular case, the high voltages can cause the insulation, which is air, to break down if the field strength is high enough. So dry air is normally an insulator, but it basically has 30 kV per centimetre to actually to break down. So if a person is connected to earth and you reach out, you're not touching it, but you're close there, you can get zapped. So that's it. It's not just touching it, it's just being in proximity to it. Another thing is the induced voltage hazard. So where there's two induced voltage hazards. One is capacitive coupling. So if you happen to be under a power line and you've got a fluorescent tube and there's a voltage difference between there, you'll actually sort of see the fluorescent tube actually operate. Now that's a very low current, and it could build up on a car, on something like a car, and when you touch it, you might jump back. Now, what you don't want to be is up in the air somewhere where you actually fall out of something. The more dangerous element is the induced voltage to do with magnetic coupling. And what can happen is you've got two long lines here. You've got one which is energised and you've got one that's de-energised. And you say, well, it's de-energised. I don't have a problem here. What's the problem? Well, what can happen is you can actually get induced currents. Induced voltages on the actual line. So remember, currents induce voltages. And if you close a circuit, you produce currents. So, so that's what the induced voltage hazard. So that's the other danger. The other one is step and touch voltages. So again, you're not actually touching the conductor, but what's happening here is you've got a fallen line. So if you happen to step close to that, and what you can see here is you've got these potential lines. What's actually happening is the current's going into the earth. Now the earth has a certain, not resistance, what is it? Resistance equals phi, what's it called? Resistivity. Resistivity, yeah. It has a certain resistivity. So, like anything, so therefore, it's to do with the area. The area relates to the resistance. So if you've got a small area and something is going through it, you'll get a higher resistance. As the area gets bigger and bigger, the resistance goes lower and lower. And that's why close to the source, you actually get the gradients of voltages. So here, this is a case of step potential. So you can just be, again, you're not actually touching anything, but you're close to it. And if your feet are actually sort of spread apart, then you can actually get a voltage difference, you know, of a couple of kVA, which can then create a current. So that's what's called step potential. Now, if you touch something, again, you sort of think, well, okay, I'm touching something, I'm going to, you know, that's pretty bad. But what's actually happening is you're touching something, and it's all to do with the relative voltage between your feet and your hand. So this might be 12 kV, but on your feet it's 10 kV. So you'll get a touch voltage. Now this is very, very important as you start looking at substations and things like that. So again, have a look at the electrical power system safety rules. Have a look at what they talk about there. It's really, again, it's just a guide. It's just giving you some extra information. And if you ever go and do a job interview with Western Power, it's good to sort of at least have looked at things. You can also get a voltage potential rise back at the substation. So the key thing with any fault is the fault has to return. It has to close a loop. So for current to flow, you have to close a loop. In this particular case, usually what you're doing is coming back to a substation, which has got its little earth grid. So what's happening is the fault current's going along there, into the ground, back through the earth, and back to the substation. Now what actually happens is the voltage rises. Again, it's to do with this resistance. So close to the actual fault, you'll get quite a big voltage change. But as you go, as the current's going through a bigger and bigger area, the volts don't change that much. But then when you come back to its source, it has to sort of refocus, reconcentrate. So that's why you then get this EPR in the substation. So again, it's a nice little V equals IR diagram, and you can sort of see roughly what's happening there. So in a substation, usually we actually have these grids. So there's actually buried copper, and what that's trying to do is reduce the potential as you walk away from something, to try and keep your potentials quite close together. And what you can see here is someone's done something here where you've got a fault in the substation. It's going back out of the substation, but you can see here, the voltages are different depending on where you are. So again, it's this issue of if you're touching something that's at 5,000 volts and something else is 4,000 volts, you'll get 1,000 volts between you. So here, touching something or even walking across here, you can see you can get a voltage difference. So that's step voltages. So we've talked about the hazards. Now we can just talk about controlling the hazards. Well, there's lots of things that we help us control the hazard. One of the fundamental standards that people use, and again, look that up if you can, is AS2067, which is to do with substations, high voltage installations. It's the wiring rules, you might say, of high voltage systems. Also, have a look at you've got so much stuff out there to look at, but these are really the important ones, just to get an idea. So obviously, controlling the hazards, some things we use are mandatory training, access permits, danger zones, minimum approach distances, earthing, equipotential bonding, and the substation design. So substation training is a requirement of Western Power. So before you go into a substation, you have to actually go through a training. So this is me, or well, not me, but going through a training exercise. Also, there are access permits, which means you just can't walk in to actually go and do anything. There's a strict regime around doing any maintenance work, and that's all to do with ensuring that everything is isolated correctly and before you actually go and work on it. So you'll hear about this thing, access permits, when you work in industry. So power lines, there's a standard which really says anyone who is not an authorised person or hasn't been trained, it's about these danger zones, staying out of the danger zone. So if you've got a normal high voltage down the street, it's 3 metres. If you've got a transmission line, it's 6 metres, and a metre with low voltage. And so people are doing work around there. The key thing is you have to stay out of that danger zone. That's considered to be safe. So when you're working with high voltage, there's also a minimum approach distance that you have to rely on. And you can only do that if you're an authorised person. So usually electrical engineers will go through a safety training and they'll be authorised to be able to approach whatever that is, whether that's a bus bar or whatever. And you can see here, again, the distance varies depending on voltage. Obviously, the higher volts, the more it can jump, so you obviously want to stay well away from it. And only specially trained, authorised live line people can actually go within this in this area. So this is trying to keep people out of a zone of hazard. That's what this is all about. And again, if you're working with high voltage, that's something you've got to actually deal with. So one of the things that, again, we've talked about issues with induced voltages, or someone accidentally shuts the circuit breaker. When people are working on lines, they're actually creating, what they're doing is earthing everything and creating an equipotential area. So what they'll do is they'll earth both sides of the transformer before they go and work on it. So that's creating a safe, if someone accidentally turns on a circuit breaker, it'll go into there and straight into earth and trip the circuit breaker. If there's any induced voltages, again, it's doing that. These sticks are highly insulated, so it's a way you do that. And you can see they're actually joined together here before they get driven into the earth. In substations, they actually use, because the substation itself is all earth, it's all connected together. Here they're actually earthing a line, actually to the pillar, but that's actually earth to everything else. So earthing is one way in which we reduce the hazards in high voltage situations because of induced voltages, accidental re-energisation, things like that. So we've talked a little bit about substation earthing and how important it is. And it's all about trying to keep the potential so that when you're touching something, that the voltage difference between the two parts that are touching things is minimised. So this is, you might even see them out in the suburbs around a pole with a switch. So here is an earth mat. It's just an, but what it's done is it's actually connected. It's connected up to the earth system, and then this earth goes up to the actual switch or whatever it is. So what it means is if you're actually holding the switch, it means that as close as possible, your hands are at the same potential as your feet. Now, if there is a flash and there's some sort of discharge to earth, it'll run down the pole, but it'll also run down, your copper's much more, that might be, 0.01 of an ohm versus you. So even though you're actually connected to it, again, old parallel paths, you'll actually, it'll bypass you. And also, you can see here, things are all connected together. And that's all to do with reducing step and touch potential. So if you go into substation world, you go into industry, you'll find you'll hear about this step and touch potentials. So it's there. But they're the sort of things that are happening. So I guess the key points of this lecture really is getting back to you that electricity is dangerous. Now, it's probably as a profession, it's probably no more dangerous than you being a Formula One driver. I don't know, but it's just the reality of it. You're not going to be exposed to it every day, but you'll be out there. You'll want to get out there to look at stuff. So where do we inspect it? Just inspecting things can be looking at, they're hazardous. It's just, you might just be inspecting something and you just put your finger in there or your camera. That's the other danger thing. You've got to be careful with your cameras. You want to look at something, you put your camera in there and suddenly it connects to something. So we've talked about what are sort of the hazards. So be safe, it burns, electrocution, shock, arc flash, fire and explosions. So that's a good way of, they've put together a bit of an acronym to sort of to explain the hazards. So electric shocks, current level, we've talked about that. Up say 100 milliamps, you've got to anything above 30 milliamps. Now that 30 milliamps is an interesting number because it comes back when you look at RCDs and you'll find that it'll actually try and trip it below 30 milliamps. That's the reason why. So this is the reason why they're actually designed that, and I can show you a little bit more about that. So there's reasons, all this sort of stuff. This is the the background to why you think why is an RCD set to 30 milliamps, and you think, oh, why is it? Well, you actually find out that that's why it is. So we've even looked at an electrical model, nice simple Ohm's law one. And you'll be amazed at how much you use Ohm's law, so make sure you know it. So we've also looked at some electrical shock hazards, especially in switchboards. So hopefully you've got things like capacitors. They might be live. We talked about, I didn't talk about batteries. Batteries can also, when you've got large numbers of them, so this is where you start getting, these battery energy storage systems, the big ones, they can have 120 volts, 200 volts sort of thing. So they've also got acid. There's other things as well. So we've talked a little bit about controlling electrical hazards. So the key thing is to be aware of these things. This is just an awareness, and hopefully when you do get employed, you'll actually go through a whole electrical safety thing as well. But at least this is a starting point. At least you'll actually know a few of these terms, step potentials, touch potentials, how the body, how you do get electrocuted, that it actually is such a low value. And when we looked at some high voltage things about, well, okay, there's a line there and a line there. This one's energized, this one's not energized. I don't have to worry about it. Whoops, wait a sec. And the number of accidents that have occurred like that because people haven't realised that you can get a voltage occurring there. So we've talked about that, and but my advice, it's good to go and have a look at the electrical safety manual. Flick, it's got all these pages. Just flick them through. Just have a look at, have a feel of it. It's just a good resource when you start thinking about understanding safety. Western Power one's a good one for HV. It's just it won't take you very long. At least you know where to look. And also get into this is the DMERS site. It's just a way of getting in there, and you can start to see there's actually electrical bulletins, safety bulletins, and all sorts of other stuff that occur there. So that's end of lecture 1. Thanks for your attendance. Hopefully, again, it's all about things that you've just started to look at, because you will see these things in real life. So, the next lecture we'll do is about this arc flash issue. Again, it's just being aware of it. That when you go to a switchboard, you think, okay, you know, I don't drop tools in there or do things. We'll explore that a bit more anyway.
All right, let's thank Craig for.
Yep. Thanks. Good. Okay, go home and do all your study now.
So I think that brings this lecture to a conclusion, and we'll meet you all again next week.
Is lecture 2 for the safety going to be next week?
We haven't planned that yet, but I will do I'll start the next chapter next week.
Is there a better week for you? Is it, you know, to avoid the exams and midterm exams? Anyway, look, you know, you've got your world's your oyster. Go and look, go and just grab those. You at least know where to look, and just, you know, you don't have to do it now, but just you've got them available. One thing you've got to think about as electrical engineers is developing reference material. Now, everyone thinks they can just Google anything. The tricky part is that
Figuring out
what it is, but also things stay online for a while and then they disappear. It's happened to me over the last 10 years. I've looked for something and yeah, I've seen it there, and then for whatever reason, you know, it disappears. So grab them. I mean, you know, the Western Power ones will be there and things like that, but the other one, which I thought was very good, the Electrical Safety Manual, it just gives you a feel of, okay, this is industrial stuff. This is what you might think about. Oh, they've got things about RCDs there. It's just a very useful, compact guide about sort of what industry looks like. Okay. Thank you.
Thanks, Craig. Thank you. Here. So I think we have to do the thing for this lecture. Yeah. Now,
So this is 1 hour. You have to tell the room.
that you done a lecture for 1 hour, so I'll ask what paperwork for that, because you already enrolled
Oh yeah, I'm already so I'm
in the
already
system,
in the
right?
system,
You're
yeah.
already in the system.
Just knowing how that works.
Yeah. So there's a basic rate, they pay for
Yeah.
hourly rate for the lectures, and you do that, and then you put another claim for the other one that you do. Yeah, thanks.
Sorry, just really quickly. I saw the assignment got released a couple of days ago. When is it due? Do you know?
I think it's due on Wednesday, no?
This Wednesday? This coming Wednesday?
Not this Wednesday. When is
I think it's next week Wednesday.
next
In
week
1 week's
Wednesday?
time.
Next week
No, we
Wednesday.
can.
Well,
It's pretty heavy.
it's hard, then if it's hard for everyone, maybe you request a
Do we
extension.
speak to Lou Jennifer what the
Yeah,
extension? I think he
just
released
send
this,
him, maybe he will give a blanket extension. to
Yeah, because he
everyone.
only released it this Monday after the
Yeah.
study break.
Yeah,
Yeah.
so maybe we can do an extension. Just
Okay, I'll
send him
speak to
an email and tell, can you extend the deadline?
I think a lot of students have been complaining about that.
Oh, is it? Okay.
Everyone has exams and other assignments, so we're not able to start until
All right.
next week anyway.
You can't start till next